copper turnings react with dilute nitric acid according to the following balanced equation. So you've got 3:8:3:2:4. Student adds a certain mass of copper to a beaker containing that many decimeters cubed of that concentration of nitric acid. So first we have to define molar mass. Again, this is a definition. You don't need to know them off by heart. And it is in your notes. Molar mass is the mass of 1 mole of any substance given in grams. Then calculate the number of moles of each reactant. So the first one of the copper, number of moles is equal to mass over molar mass. They've given me a mass of 19,05 grams. The molar mass of copper is 63,5 grams, so it's 0,3 moles. Then for the nitric acid, which is the other reactant, you're going to go number of moles is equal to concentration times volume, and that is 1,4. And your volume is already converted into decimeters cubed, so it's 0,5, and you have 0,7 moles. Now it's 3:8 in terms of a mole ratio. I've got 0.3, but I don't have 0.8. So I am going to run out of nitric acid first. It is going to be the limiting reagent. I am going to have less of that. I'm going to run out before. Anyway, that will end up being my answer to 2.4. 2.3, how many atoms are there in that mass of copper? Well, I know how many moles there are, so I can calculate the number of atoms. Number of elementary particles is number of moles times Avogadro's number. So it's 0,3 multiplied by 6,02 times 10 to the 23. And I'll end up with 1,81 times 10 to the 23. And what are we talking about? We're talking about copper atoms. Determine which is the limiting reagent. 0,3 moles of copper should need 0,8 moles of nitric acid. But I don't have 0,8, I've only got 0,7. So that is going to be limiting, and that is my nitric acid that is limiting. You could have divided 0,3 by 3 and seen what answer you get. Divided 0,7 by 8 and seen which of those two is going to give you the bigger number. And the bigger number comes, obviously, you get 0,1 here. Here you get 0,08 something or other. 875, I think. So it turns out that you do not have enough of the nitric acid. 2.5, calculate the mass of water that is produced. So since we have a limiting reagent of 0,7 on the nitric acid, so the nitric acid is my limiting reagent, so I can only use that number of moles that I've got over there. And I'm going to say, so I will use the nitric acid, and I'm going to go mass is equal to number of moles times molar mass. And my number of moles I am going to get by saying the ratio between nitric acid and water is 8:4. But I don't have 8, I have 0,7. So therefore I'm going to get 0,35. 0,35 moles multiplied by the molar mass of water, which is 16 plus 1 plus 1, which is 18. And that turns out to be equal to 6,3 grams. Once the percentage yield of nitrogen monoxide or nitrogen 2 oxide if 3 decimeters cubed of nitrogen monoxide is obtained at STP. Well, firstly, how much should you get? Again, I use the nitric acid because that's my limiting reagent to get my mole ratio. And I'm going to say 8:2 from the balanced equation. But I don't have 8, I have 0,7. So that's 175, 0,175. So what volume should I get? Number of moles times molar volume. And I should get 3,92 decimeters cubed. But they tell me that I didn't get 3,92, I got 3. So 3 out of 3,92 times by 100 is equal to a 76,53% yield. A solution of nitric acid is made by dissolving 0,2 moles of the liquid acid in water to form a 0,5 decimeters cubed of solution. Calculate the mass of nitric acid that would need to be dissolved. So I am going to say mass is equal to number of moles times molar mass. The number of moles that they've given is 0,2. The molar mass of nitric acid is 63. Nitrogen, which is 17, plus hydrogen, which is 1, plus 3 oxygens, which are 48, and you land up with 12,6 grams. Determine the concentration of that solution. Concentration is number of moles divided by volume. 0,2 they give me, 0,5 they give me, and it's 0,4 moles per cubic decimeter. Or if you wanted, 0,4 capital M, which is molar. I've got a diagram here which shows part of an atomic lattice of a diamond. In a diamond, every single atom is bonded to every single other atom. It forms a huge molecule. In other words, it's a covalent bond every single time. So these are sharing electrons. It's very, very strong. And there are millions and millions of carbon atoms. They first want you to define a covalent bond. And again, learn your definitions. You can look it up. A covalent bond is atoms joined by sharing electrons or the overlapping of orbitals. Explain why a diamond has the highest melting point. A covalent bond is an exceptionally strong bond. The entire lattice is covalently bonded together and therefore very difficult to separate or to detach the solid particles. Break up the lattice, in other words. 3.2.1, we've got a crystalline structure of boron nitride. So if you take a look, boron 3 nitrogens, boron 3 nitrogens, boron 3 nitrogens kind of thing. And define the term electronegativity. Again, it is a definition that needs to be learned. It is the tendency of an atom to attract a shared electron pair within a bond. Using electronegativities, determine the nature of the intramolecular bond. In other words, not the intermolecular force, but the actual bond. Is it covalent? Is it ionic with boron nitride? So let's go. Boron, the electronegativity is 2, whilst nitrogen, the electronegativity is 3. So that electronegativity difference is equal to 1, which would make it less than 1.4 or 1.7. So it's a polar covalent bond. The table below shows the melting points of sodium chloride and magnesium oxide. Explain why these melting points are so high. Both of them are ionically bonded substances. So they're both between a metal and a non-metal. So they are ionic bonds, and therefore an ionic bond is between a positive and a negative particle, and it is a strong electrostatic force. And you either need to use the word electrostatic force or coulombic force. Both of them mean the same thing, which is attraction between positive and negative. If you've got a strong electrostatic force, you're going to need a lot of energy in order to break it. So you're going to say lots of energy required to separate lattice. Separating the lattice means you've now got a liquid, which is melting, and that's lots of energy over there. The table below shows the boiling points of the group 6 hydrides. And the first one's water, then hydrogen sulfide, hydrogen selenide, hydrogen telluride. And as you can see, the melting point is going to get, first is this 100, which seems weird, because after that it's minus 60, and then it's increasing, minus 41, minus 2. So water seems anomalous. In other words, it does not fit the pattern. Name the intermolecular force that exists in hydrogen sulfide. That is going to be a dipole van der Waals force. And then in water, you should by now know that water is one of the 3 examples of a hydrogen bond force. And it's horrible because there's this word bond when it's really an intermolecular force. Hydrogen bond force is an intermolecular force. Explain how a hydrogen bond force is formed. And now you need to think carefully about these words, but you need to have the fact that hydrogen, so your hydrogen bond force is when a hydrogen bond is bonded to either nitrogen, oxygen, or fluorine. What's special about these NOF gases is that they have a very high electronegativity. That creates a very small, these are small and they're highly polar. So it becomes small and polar, and therefore they are very close together, they're very strongly attracted, and therefore you get a very strong, anomalous is the word I was using earlier, but a peculiarly strong intermolecular force. Then it asks you to consider the other 3 molecules and explain why hydrogen telluride has got the highest melting point of these. And the reason that you want to give there is that it is a big molecule compared to the others, and therefore you have the greatest electron cloud wobble, and that electron cloud wobble results in a more polar dipole, and therefore stronger IMFs.